So welcome everyone. Welcome to Keep Talk. This is our session number 2. I am your host for tonight, joining from Austin, Texas. This is our second session. As I said, our first session was on cybersecurity, and we had a basically basic talk on cybersecurity, and we are going to explore more in about 2 to 3 weeks. The reason we started Keep Talk because we wanted to, it is impossible for any of us to learn, read all the books. In a few minutes. Before that, I would also like to know what's coming up in the future for us. So we have done cybersecurity. Next is, after this session, we'll do quantum mechanics and quantum computer and computation and how it's changing the world. We are going to have a speaker on 5G, how it's going to change our world. Industrial Revolution 4.0, cloud computing, how SDV and drones are going to change our life, which is self-driving vehicles and the drones. So we do have subject matter specialists for all these topics. So hopefully you will be able to join us in the future. It is good for kids, adults, and all ages. So I welcome you to join us every time you see a session going on. Now, few things about the session. One, this session is being recorded. If you do not like or do not want your picture to be on, please turn off your video. We request when the guest is speaking, please have your microphone off. There is a button, it says raise your hand. So when the Q&A time comes, you can ask your question 2 ways. One, you can click on chat and put your questions in there. 2, you can raise your hand also. There is an option. You can do that. You can speak to the guest directly one-on-one. But I request you again to minimize any background noise. Please unmute your microphone. Once we are done with the Q&A, then you can directly also speak to our guest speaker for tonight. And that will be an open session. We'll unmute everyone and you can talk one-on-one and have a hangout whenever you want to. Now, this topic, I am also, do not know much about it, but I know we have a guest speaker who is very fluent in this. He's lifelong, he has been there for 30 or 40 years, I believe. Today's on quantum mechanics, Einstein theory, and all this he will be talking about. You have heard about quantum teleportation. So I know a little bit, many of you know a little bit, but today we'll know more from our guest speaker. And we'll also can dig into details if you have any questions in the Q&A section. A few things that I learned yesterday. I knew that the only thing I knew is spherical. Now, many of you are thinking, what is the shape of our universe? And the first thing comes into our mind is spherical. But in reality, it is more complex than that. Maybe we can grasp, maybe we cannot. But our guest speaker will also talk about that. Is our universe a giant computer simulation? We'll talk about that. Are we all part of virtual reality? What is teleportation? How can we test this? Things like that we'll get to know today. As you can see, Professor Shafiqur Rahman. He is a professor at Allegheny College. I had to, by the way, Google this, how to say Allegheny or Allegheny. So I watched the YouTube and they said Allegheny College. So I hope I am right. I'm not saying it wrong. He's still a professor in this college. A little bit about his background. Shafiqur Rahman is a professor in the physics department. His current research in the areas of statistical physics. He has done research for many institutions, and he also earned 3 prestigious Demler Awards for his innovative teaching. I'm not reading all the things that you see, but you're most welcome to ask for a copy and we'll send it to you. He recently received, very interesting thing, he recently received a grant from the Mellon Foundation to write a romantic novel based on his memories from the Cold War, East and West politics, and his love affairs with his wife. He received his BS degree in physics from Germany and his PhD from Northwestern University. And without any further delay, let us welcome our guest speaker for tonight, Professor Shafiqur Rahman. Professor Shafiqur Rahman, I welcome you, and we are looking forward to, you can start your session, and go ahead, please.
Thank you. Thank you for that generous introduction. Today, I want to discuss some of the astonishing things going on in physics that will change the way we live in future. Things that are so bizarre that when I explained these one day to the dean of our school, he simply said, these are just pure magic. So let's start. I'm going to use a PowerPoint presentation. So you will not be seeing me, but I will use that presentation and will explain different things that are in there. And if there are questions, then as was mentioned, you can ask me at the end. So okay, I'm assuming that everyone can see it now. The title, Reality in the 21st Century. And I will discuss several topics, but also whether our universe is a massive computer simulation. So the outline of the talk is as follows. We will talk briefly about the reality in the previous century. And then, of course, the main part of the talk. And finally, some conclusion. So in the previous century, the big changes that science brought about, there were really 2. One is Einstein's relativity theories. You probably pronounce it as Einstein, but the correct pronunciation of his name is really Einstein. Just like in Bengali, in German, names are often a combination of 2 words. So Einstein is, Ein is one and Stein means stone. But of course, that's not what the full name means. The full name doesn't mean anything particular. Anyway, so his relativity theories and then quantum physics. For the bulk of today's talk, I'm going to cover the following topics: quantum teleportation. I will briefly mention quantum computers because there is a speaker coming up next week who will discuss this in detail. Very briefly again, quantum cryptography. I will not go into any details of these 2. I will talk a little bit about quantum information theory because it gives us an insight about how the universe might come to an end. And then finally, about some tantalizing facts emerging that suggests that our universe might be a massive computer simulation. So let me begin by talking about Einstein's relativity theories. He really proposed 2 different theories. The first one was special theory of relativity that deals with motion. The astonishing thing that came out of this is that time passes more slowly on a moving body. Also, that means that if you are on a fast spaceship, then time will pass slower for you. That means you can travel to the future. So these are not conjectures. These are known things. In fact, your cell phone, your computer would not work if the special theory of relativity were not valid. Then the general theory of relativity. Some of the astonishing things there were the fact that space is curved. Later, it emerged from that theory that there are black holes. And one can use these theories to look into the issue of time travel to the past. So I want to make this very clear to everyone. As far as the special theory of relativity is concerned, traveling to the future is possible. We know that that is valid. The only thing because of which we may not be able to do it yet is simply we need a very fast spaceship. Traveling to the past is a little more murky. The theory seems to suggest that we can do it, but there are other issues. If I have time, then I will briefly mention that. Now, these two theories, they brought about a total paradigm shift. This is a word, paradigm, or rather the phrase paradigm shift. Philosophers love this. It simply means that it introduced a profound change in the way we think about our place in the universe and the universe itself. It was totally different. Then quantum mechanics was also introduced in the previous century. In fact, Einstein's Nobel Prize actually is a part of his work in quantum mechanics, the early quantum mechanics. One very interesting thing about Einstein is that in 1905, he published three different papers on three totally different topics. Now, typically in sciences, that's not how it works. People work in an area and they publish in that area. So what happened is the following. When Einstein was working on his PhD in Germany, to get a PhD is really not an easy task. You have to make a proposal, and those proposals are routinely rejected. So what happened with Einstein is that he submitted a proposal, it was rejected. He submitted a second one that was rejected. The third one was accepted. So he kept on moonlighting, he kept on working on those other two, and so he ended up publishing all three in the same year. The interesting thing, though, is that he did not get the Nobel Prize for his work in relativity. Relativity was a bizarre new idea. It took many years before it could be verified. And so he won the Nobel Prize much earlier than that for one of the other works. Now, for today's, one of the main topics, namely the quantum teleportation, I'm going to have to introduce some basic ideas: superposition, entanglement, and decoherence. So superposition, it simply means that if you have an object that can exist in two different states, then it can also exist in a what we call a coherent superposition of these states. That means the state of the system is a combination of the two. To explain this fully, let's consider the famous Schrodinger's cat paradox. So what we have is a cat that's in a sealed room. The cat is alive when it was put in there, and there is a vial of poison hanging from the ceiling of that room. That vial can be triggered by some radioactive trigger, which has a probability of 50-50 at any given time. So the question is, sometime later, what state is the cat in? Now remember, superposition principle says that if something can exist in two different states, that it can also exist in a state that's a combination of the two. Now, if you look at this particular symbol, this line and then the greater than sign, this is used to indicate a state in which the particle is present. So according to quantum mechanics, the state of the cat is both alive and dead. In fact, it gets more complicated because these two states, they are multiplied by some constants that are functions of time, which means that the cat could be 40% alive and 60% dead right now, and later it could be 90% alive and 10% dead. In fact, things get even worse than that. This C1 and C2, they are what we call time dependent, that has been shown here, but complex functions. That means these are not just real numbers, rather they have a real part and an imaginary part. So it's a complicated description. So let's consider that you have actually been put in a room that has two doors, no windows, and you go out of the room. So we would say you go out of the room either using door 1 or door 2, but quantum mechanics says you go out through both doors, because it is possible for you to go out through door 1, and it's possible for you to go out through door 2. Right. So strange as it may sound, there have been some old experiments, and there has also been a recent experiment. It verifies that this is actually true. So the examples that I gave about the cat and you being in a room going out through a door, we know that these examples are absurd. The cat is either alive or dead, and you go out through only one door. So how do we reconcile this? We reconcile this through a concept called decoherence. It simply means the so-called loss of coherence. I'll explain this in a moment. Between components of a system, components simply mean the states, the two states that we talked about, or even larger number if the system can be in large number of states, right? So if you look at this diagram here, notice that if we consider this to be this here, these waves, to be alive, this dead, they're traveling along this direction, it's time, they're coming together, and so we have this complicated situation where it is alive, dead, real, imaginary. But eventually, if due to decoherence, it loses that coherent state, then it is either in the alive state or dead state. So how does decoherence come about that makes this system fall into one of the possible states? It happens when information leaks to the outside. So for example, in case of the cat, we could set up some detectors outside that looks at transmission of heat through the walls. So if there is transmission of heat coming through, we know that the cat is alive, its body is producing heat. But if we could really seal that room so that no information can come out, then the cat would actually be in that superposed state of dead and alive. So decoherence is a very big problem. Basically, the two examples that I gave you, they're absurd simply because of decoherence. The person goes out through door 1 or door 2 because we cannot contain that information. For very small particles, this superposition plays not only a role, but unless we take that superposed state into account, the answers don't come out right. So next, I want to introduce the idea of entanglement. This is the most important property for quantum teleportation. So let's consider a particle called a pion. Now, a pion is an unstable particle. A little later, it decays. It decays into an electron and a positron. So the left one, we would normally think it is either an electron or positron, and the right one, depending on what this one is. If the left one is electron, then the right one is positron. And the reason that they have to be complementary is that a pion has 0 charge, electron has negative charge, positron has positive charge, so that the sum is also 0. So when a pion decays, if one of the particles is electron, the other one has to be a positron. So now the question we ask is, which one is the electron and which one is positron? Now remember that these two particles, this electron, positron, right? When the pion decayed, then we cannot be sure of the issue of electron or positron. In fact, because this particle, the one going to the left, it could be an electron, it could be a positron. It is really in a superposed state. So each particle is a combination of both. This is what we mean by entanglement, that two particles that have complementary properties, only in the sense that unless they have been looked at, they are a combination of both. So in that situation where they are a combination of both, we say that they are entangled. This is the property that we are going to need to do quantum teleportation. So let's talk about quantum teleportation. It basically is simply moving an object from one location to another without the object going through space. So it vanishes at one place, shows up at another. Now this diagram is actually from Scientific American with the idea of Star Trek that probably all of you are familiar with, where they say, beam me up, Scotty. So how is quantum teleportation done in real life? Now, we cannot do it with a macroscopic body like man, but just to explain it, let's say we want to quantum teleport this object. Then what we need are a pair of entangled particles. So this particle and this particle, they were created in a way such that they are entangled. So please remember that each of them has that dual property. So the next step is to entangle these two. We know how to entangle things. There are optical setups which can take two particles and create a combination where each particle has lost its unique property, but shares property of itself and the other one. So you know how to entangle. So the interesting thing is that the moment you entangle these two, this particle here has become that object. And this particle which was not entangled, that one and this one, as we said, we entangled them. So they are now an entangled pair. So this is the basic idea of quantum teleportation, and it is routinely being done in the lab at this point. Now you will see, when we look at the history, it is very difficult to achieve this because of decoherence. We cannot keep the information locked. We cannot keep it confined. And therefore, eventually, the particles, they lose their combined identity. So originally, the idea was proposed some 27 years ago, 1993. In 1997, physicists were able to do quantum teleportation using only one property. So they were able to teleport not an object, but the property of an object. And the property they used is polarization. So for those of you who are not familiar with polarization, if you consider a light particle, it is an electromagnetic wave. And if you look at this blue wave, that's the electric part. And let's not worry about the red one, that's the magnetic part that's at right angles. But the important thing is, if you consider the blue one, then that plane in which we see those waves, that plane represents a polarization. So you could have a polarization like this one, which is vertical, and you could have another ray that has horizontal polarization, and you could combine them in different degrees and thereby get any kind of light with any degree of polarization. So when we talk about pure polarization, we can think of a wave like this. At this point, this was actually achieved a couple of years ago. This quantum teleportation of one property has been done over a distance of 700 kilometers. In 2013, people were able to teleport an atom, a very small atom, over a distance of 50 centimeters. 2015, 2 properties were teleported, and last year, 3 properties. So it is still in very infant stage. To go to a macroscopic body like a cat, we don't know when that might be possible. But it's an issue of engineering problems, not of physics. Physics says it's possible. So what are the implications, the immediate implications? One would be, a simple example would be cell phone conversations. So for example, if you are talking to someone that sound waves from your voice that is converted into electromagnetic waves, and those are sent to a satellite and then it is beamed back. Now, because it goes through the atmosphere, because of atmospheric turbulence, there can be problems. You may get the message not in pristine condition. But what if you could quantum teleport the message? It would disappear where the speaker speaks into the phone, and it would appear where the receiver gets it. Then there can be no change. It is an exact replica. And therefore you can teleport conversations without any degradation. So that's a possible application that may not be too far away. And this issue of beam me up, Scotty, as I explained, because we are dealing with macroscopic bodies, so you will need, if you want to teleport, let's say 5 atoms, a cluster of 5 atoms, you are going to need clusters where you have 2 5-atom clusters that are intertwined. That's not easy to achieve. It is possible, but clearly for a macroscopic body where you are talking about billions and billions of atoms, we are talking about some serious engineering issues. So in principle, beam me up, Scotty, may be possible someday. I think I went one slide too far. Okay, so quantum computers. As I mentioned before, I'm not going to discuss this today because another speaker will talk about it. If you consider your cell phone, then the memory, you are probably talking about some gigabytes. But consider a quantum computer that has only 12 quantum bytes. If you consider a classical computer, then 12 bytes, they represent 3 integers, that's it. But if we can have a quantum computer that has 12 quantum bytes, just 12 quantum bytes, that is sufficient to crack every bank code in less than 1 second. So that's the kind of power we are talking about. US government has actually given large grants to different groups to develop quantum computers. Every developed country is trying to develop quantum computers. Quantum cryptography, again, I'm not going to get into details. I just want to give you an idea of what it is. Let's say Alice and Bob, they want to talk to each other over secure channels. They don't want people to eavesdrop. Now, normally, if they send the information and somebody eavesdrops, there is no way for Bob or Alice to know that the information has been compromised. However, it is possible by using quantum channels. It is possible to use quantum cryptography. There, if it has been compromised, then it is possible to make a detection. It is possible to detect that the information has been compromised. In fact, this kind of quantum cryptography has been in use for many years now. For example, the results of elections in Sweden, they are routinely sent by using quantum cryptography. That way they can be 100% confident that the result has not been compromised. So next I want to talk about quantum information theory, because this gives us a nice idea about how the universe might come to an end. The interesting thing is that in quantum mechanics, information itself is an object. Just like you can consider properties of an object, you can move the object around. It can have very bizarre properties. that we will get into in a moment, like an object. It behaves like an object. I want to introduce the idea of disorder. Now, this is actually not difficult to understand. If you want increase in disorder, just add heat energy to the system. So that way, what will happen is that the atoms will start moving more than before because the body is hotter. And so clearly that gives rise to more disorder. So in physics, we call this entropy, and this is the exact definition. So it's not just the amount of energy you add, but also at what temperature of the body you are adding. Both of those determine the exact definition. But for our need, it is sufficient to understand that if you want to increase disorder, you just add heat energy. And so if you want to decrease disorder, you remove heat energy. Now, the second law of thermodynamics says that the total disorder can never decrease. It can remain constant in some cases, but in general, it will increase. To explain this, let's consider the situation with a refrigerator. Now, remember that decrease in heat means, decrease in disorder means removal of heat. So what is happening in a refrigerator? You are removing heat from inside the refrigerator. So you are decreasing the disorder there. But the second law of thermodynamics says the total disorder cannot decrease. So what is happening is that the amount of disorder that is decreasing inside your fridge, the amount of disorder that's increasing outside is larger than that. So you have removed heat, put it outside, and in the process, it is not just the amount of disorder that you have removed from the fridge that goes into the outside, it is actually more than that. Because you have to do some work in order to achieve this. You cannot simply move some heat from a cold place to a hot place. So let's keep this in mind. Total disorder can never decrease. So again, this is just to remind you that if you want decrease in disorder, heat energy has to be removed. So now let's talk about what happens to disorder when a computer disk is erased. Now, if you have erased the computer disk, one possibility is that you put random bits, but it is also possible that you put, let's say, all ones in there. So clearly, you have decreased the disorder when you erase the disk. Now notice, decrease in disorder is equivalent to heat energy being removed. So you have to remove heat energy from the computer disk or the computer system. That means the computer system must release heat to the outside. So it doesn't have to be a total erasure of the disk. When you delete a file, the same situation happens. Now, as you know, heat flows naturally from hotter body to colder body. So what will happen is that as heat is being emitted, work is being done that can generate heat that moves from hot to cold. Eventually, there will be no temperature difference. The universe will come to a thermally stable situation. There is no heat differential. But the third law of thermodynamics says that you cannot operate engines without temperature differential. In fact, the efficiency of an engine, the formula, some of you might know, Carnot's engine, the formula for efficiency, that has the two temperatures, that has the ratio of the two temperatures between which the engines will operate. So if we wait for a very, very long time, what is going to happen is that the amount of computation that is being done, it will give rise to more and more heat being released. The universe will have less and less differential in heat. And eventually, you will not be able to operate any engine, whether that's computer or any other kind, because there will be no temperature differential. That means there will be no more computation. In fact, people have actually worked out details through some other means about the maximum amount of computation that can be done in the universe. There is an upper limit. And so at that point, the universe dies. So I hope that you find this idea intriguing. I certainly did. And now we come to the topic whether our universe is a massive computer simulation. There is a technical phrase, simulation hypothesis. It says that all of reality, including you, me, the entire Earth, and the rest of the universe, is likely a computer simulation. So that's the hypothesis. How do we prove it, or how do we know? Okay, so here is now a question to everyone. I'm sorry that I cannot interact with you through this, and therefore I will simply ask you, in your mind, tell yourself, what movie is this from?
Matrix.
Yep, that's right, that's right. That's right, it's from the movie Matrix. But what is the Matrix? What is that thing? What is the Matrix? Matrix is a simulated reality, right? So it's a virtual reality that has been created by machines to subdue the human population while their body's heat and electrical activity are used as energy source. But remember, what we have in Matrix are the following three things. We have the machines, the robots. Then we have that simulated reality, but we also have some people in the actual reality, right? So there is a real reality and a virtual reality. So now comes the next question. The Matrix, it came out in 1999. But what is the name of another science fiction movie with the same idea? Things happen in virtual reality that also came out in 1999. In fact, these two movies, they competed with each other for the top science fiction prize, and The Matrix won it. This movie is not that well known, so you may not really know the name. It's called The 13th Floor. So this picture is from the cover of the DVD. So in what way is the storyline different in The 13th Floor? The movie opens in the 1990s Los Angeles, where a company has developed a virtual reality game. The game has simulated people who have feelings, who interact with each other. So what we have here is somewhat like Matrix. We have a reality and a virtual reality. But this movie is actually more complex. The main hero of the movie realizes later that he himself, that's the 1990s LA, where he created this simulation. He himself is a simulation. Now, one of the interesting ideas here that shows up in this picture, notice he realizes that any simulation has to have a boundary. It cannot be infinite. Even the universe may not be infinite. So he takes a road and continues traveling on that road and arrives at the end. So that is the end of the virtual reality. He's looking at the border. He's looking at the edge of virtual reality. So this is a much more complex movie because what we have here is a simulation within a simulation. Now that's just to have a little bit of fun. So what about the more serious issue? We will discuss some reasons as to why the possibility that our universe is a simulation is actually quite high. I'm going to show you a short video clip that discusses 5 reasons, and then I will show a few other reasons. Let me warn you, number 4 and number 5 are very technical, and they have not explained it well, but I will come back to that further down. Okay, so you saw the first 5 reasons. Now I will introduce a few more reasons as to why our universe could be a simulation. So number 6 is the probability. Even if you consider today's universe, we human beings, we are performing many simulations. Some of them not so sophisticated, but some are. For example, the video games, they have improved substantially in terms of their virtual reality ability. Scientists are actually able to create, with the best computers that we have, approximately 1 centimeter cube of space of the universe. That's the best we can do at this point. But if you consider civilization, as the clip talked about, 100,000 years further down, they would be able to simulate something as large as our universe. So now consider the following situation. Even today, we have many simulations running at any given time. So if we pick up an arbitrary item from the reality and the simulations, then clearly, because the number of simulations is much larger than the single reality, the probability that we will pick up a simulation is substantially larger. And then 100,000 years down, where the virtual reality could be as large as our universe, we are probably talking about zillions of simulations going on. And so among one reality and the zillions of simulation, if we arbitrarily pick one up, the probability of that particular universe being a simulation is extremely high. So simply based on probability, our universe could be a simulation. Next, I want to talk about the shape of the universe and something called periodic boundary condition. So let's consider the shape of the universe. We tend to think that there was a Big Bang, and so the universe is spherical in size. Now it is, of course, we have to understand that if that were true, even then, space would be contained within. There is no space outside. And similarly, time would be within. There is no time outside. But the thing I want to talk about is something different. Let's start by trying to visualize what our universe might be like, what the shape of the universe might be like. So let's start with a simpler case. Let's start with a 2-dimensional universe. But that 2-dimensional universe has a constraint. If it is expanded in a 3-dimensional system, then this is what it might look like. A soccer ball, for example, the surface of that ball is the 2-dimensional universe, but because there is curvature, it can be bent into a closed system that's in the next dimension. One interesting thing about this situation is that you can start at a point, continue moving in the same direction, never looking back, and you would come back to the same point. Right? So this idea that you could start at a point, continue without changing your direction, but because of the curvature, you could come back to the same point. This is something that we will need to understand. In computational work, we often use what is called periodic boundary condition. To explain this, let's consider this diagram. Let's say our system is really this central square. It has 2 atoms. But notice that when we compute properties of this, compared to the area, there is enormous amount of edge. So in order to avoid the edge effects, what we do is we make copies of this all around itself. So if we want to look at the interaction between atom 1 and 2, because that length is larger than half of this hypotenuse, we will not look at this interaction, we will look at this interaction. So this is known as periodic boundary condition. I'll explain in a moment why periodic boundary condition, but this is a standard technique in computation. Without this, your results are not very good. We call it a periodic boundary condition because if you consider this, here is the period and you just map it again and again to reduce the boundary effects. So with a 1-dimensional case, notice what we could do. We could introduce a curvature so that this end and this end, they are together. So starting with 0, but now it's not a straight line, it is curved. And then number 4 can come and join number 0 again. Right? Now look at the interesting situation here. If we did not use this periodic boundary condition whereby this point is the same as this point, then it would be flat, a straight line. But the moment we introduce curvature, we can actually meet that periodic boundary condition in this way. So you start at a point, you continue without looking back, and you are able to come back to the same point. So some scientists believe, and there are mathematical works that show that our universe might be something like this, but a 3-dimensional universe that, because of its bending, because of the curvature, it is really in 4 dimensions. Now that's something we cannot visualize. That's why I use this example of a 2-dimensional universe whose curvature puts it in 3 dimensions. So you have to think of our universe as an analog. So if that is true, that we can come back to the same point, right? Then look at the connection to what is being done in computer simulation. After all, there is no reason why our universe needs to be like that. It could be like a sphere that is continuously going outward, as we might think classically, but that's not the case. So the shape of the universe seems to suggest that we could be a computer simulation. Finally, I want to talk a little bit about so-called Planck length and uncertainty principle. Now, those who are familiar with some details of computers, you know that most real numbers can be represented exactly on computers because of how many bits are used. Of course, there are numbers that you cannot represent on a computer, even if you had an infinite number of bits. But the basic fact is that a computer, even a giant computer, even a computer from 100,000 years hence, will have a finite number of bits. Now, the Planck length is a very small length. So you can say 10 to the power minus 35 meters. Theories in physics say that you cannot probe below that level. It is simply not possible to look at, even if you had a better instrument, it is simply not possible to see within this length. So here is a tantalizing suggestion. Is it because the number of quantum bits that are being used, they are very large, and therefore this length is very small, but clearly those number of bits cannot be infinite, and therefore we cannot look at distance smaller than this. Then there is the other thing. The uncertainty principle is a well-known principle in physics, namely that you cannot measure 2 complementary properties with infinite accuracy. It's not because of any problem with your measuring system, rather it's a principle. So for example, you cannot measure the location of an object and the speed with which it is moving simultaneously with infinite accuracy. So you could get the position with infinite accuracy, but the velocity then would be totally uncertain, and vice versa. Normally what happens is that we measure position within a certain accuracy, and then we can get the velocity also within a certain accuracy. So why is there an uncertainty principle? Now, physics, of course, does not answer the question why. We simply explain nature and we say that's how nature is. But is it possible that it is because of the finite number of quantum bits that we end up with an uncertainty principle? Now comes the big question: can this simulation hypothesis be tested? In 2012, 2 groups of scientists proposed one way to test if we are a part of simulation. It turns out that there are some very high energy cosmic rays that travel through the universe, come from very distant parts. they seem to have, there are theories that have worked it out. They seem to have an upper limit, but then that upper limit is only for one kind of high energy particles. For other high energy particles, that upper limit is different. But in the distribution, namely, how many with small amount of energy, how many with a little higher, and where is the cutoff? There is some anisotropy. There is something there that is quite different from a random distribution. And these scientists, they proposed that by measuring that anisotropy, we could actually say whether we are part of a simulation. The reason being that if we are part of a simulation, then we are definitely talking about an edge, a boundary. And these ultra-high cosmic rays, when they travel, if there is a boundary that affects them. More recently, in 2017, 4 scientists, 2 of them from MIT, they have proposed several experiments. And these are based on our old friend, entangled particles. Now, these are difficult experiments. We cannot do them yet, but clearly the idea as to how to test them is already there. Now, one of the videos that you saw there, they were talking about some ultra high energy cosmic rays, the boundary, and so on. They are somewhat connected, but what we know, we don't have proper theory yet to work out the details of this, but in principle, it should be possible by calculating a proper distribution and comparing it with what we see. It will be possible to make a prediction about whether our universe is real or not. So this is after the 2012 paper came out. Lots of newspapers in this country were abuzz with the idea as to whether we live in a computer simulation can be tested. After the 2017 paper, there have also been things. Because of time issue, I'm not going into that, or details of that paper I'm not going into. So here is another little video that we want to look at.
All right, don't let your conspiracy theorist friends find out about this, but there's a scientist that thinks the Matrix is real. Hey guys, I'm Patrick Jones for Buzz60. Mind-blowing, I know. And they're testing that theory. To catch you up, German physicists came out saying that they have a theory that the universe is a computer simulation. They say their evidence is that since the laws of physics remain constant, and that there are limits to how much energy particles can have, which are limits that computer programs need in order to run. They also doubt we are the first civilization to advance far enough to be able to run universe models, meaning they really think that we're a simulation within a simulation within a simulation, and so on. So they're testing this theory by starting another complex simulation of a universe, and will check certain laws within that. The whole thing is generating a lot of negative criticism within the science community. But the researchers are optimistic and wonder if we are in a computer, if it'd be possible to communicate with other simulations considering we may be on the same platform. But please, do you think we'd be able to chat within layers of the Matrix? We can't even get compatible group text between iOS and Android. Buzz60, now you know, pass it on.
Okay, so in conclusion, our universe is filled with riddles. There are many questions that physicists cannot yet answer. The first is the quantum gravity. You might know that quantum mechanics deals with very small particles, and Einstein's general relativity theory that deals with very large lengths. So we really want a quantum theory of gravity that will be the ultimate theory. Einstein himself tried, but failed. At this point, we do have a quantum theory of gravity. The problem is that its predictions cannot be tested. Cannot be tested in the sense that they require the kind of energy density that we cannot produce in the lab. We will not be able to produce them in the lab in the foreseeable future, or even in 10, 20, 30, 40 years, unless there is a very new breakthrough that we simply cannot imagine. Another interesting thing that has come out of this new theory of quantum gravity, you might know that as string theory, is the existence of parallel universe. So in string theory, parallel universes exist. Is time travel to the past possible? We do not know the answer of that question for definite because we don't have a quantum theory of gravity. At this time, based on what we have, traveling to the past seems possible. And as I said, traveling to the future, that's an accepted thing. It can be done. We also have issues with so-called dark matter and dark energy. After the Big Bang, it is expected that the expansion of the universe will slow down. But recent measurements are showing that the rate of expansion is actually speeding up. So this anomaly made people conjecture that there might be matter and energy in the universe that we cannot see. And there are theories that have worked out details about how that can affect the expansion rate of the universe. So there are all these intriguing things whose answers we simply don't know at this point. So in conclusion, I want to tell you that physics will lead the journey to uncover these riddles. I hope that all of you will join this fantastic voyage. Some of you, especially those who are young today, hopefully will join as scientists. And those who are in other professions or will follow other professions, you can help as citizens by being interested in science and by supporting science policies. As you know, science is often under attack by politicians. As citizens, by supporting science, you can help scientists pursue this fantastic journey. Thank you.
Can I request to Soil?
Yeah, thank you very much.
And Soil?
Yes, please.
আচ্ছা আমি তোমার আক্তার ভাই তোমার আমি তো কাজ করছিলাম I was in and out, so you have the recording so that I can
yes,
see the full.
We do have the recording. I can send you the link as soon as it's posted. I can send it to you. Kindly send me your email address, or I can send it to you in Viber.
Okay, I'll send you my email address. Okay.
Sure.
Okay.
That's it. Thank you very much, Professor Shafiqur Rahman. I am guessing, at least for me, it's way, I have more questions than answers, definitely, at least for some of the attendees right here. We do have few questions. Are you ready to answer some questions?
I could try.
How long do you have? Like maybe next 10 minutes, and then we can have an open session, everybody can talk?
Yeah, sure.
Sure. So I will read it to you, and then anybody else have a question, you can also raise your hand. You can ask him directly. But on the chat session, I saw some questions, so which I am going to address right now for our guest speaker for tonight. So let me open that up just a second. So let me go back up and let's see. So one question came from Nazmul Haq. It says, if the outer portion of Big Bang has gone to disperse that have less gravitation pullback, can that portion go faster than light, and why not?
Well, in general, nothing can travel faster than light. However, there is an issue of what frame you are looking at it from. So let me give you an example. let's say you have a pair of scissors and you open the two parts and you have a flashlight on one side of the scissors, then you can go to very, very far distance where how the tip of the scissors move away from each other. That can be faster than light, but that's not an object moving, right? So this so-called phase velocity, that can be faster than speed of light. Now coming back to the question of the Big Bang, well, this is actually a question whose answer we don't know yet. On one hand, people thought that the issue of the expansion rate increasing is very odd, and therefore people have introduced these ideas of dark matter, dark energy. But very recently, a young Canadian woman physicist, together with another person, they have published a paper which says they can explain what is happening with the outer part of the visible universe that you can see. Right? Their paper is saying that they can explain it by considering the fact that at the beginning, the explosion due to the Big Bang, those matter got hurled farther away, and the effect of gravity, the so-called gravity waves, for which there was a Nobel Prize recently. So these gravity waves are catching up. That's why those outer parts are looking like they are moving faster. So that's sort of the long answer. Firstly, cannot go faster than light as far as material is concerned. And secondly, at this point, we really don't know whether it is the material, the dark matter and dark energy, or whether it is because the gravity waves have not been able to catch up that we see an accelerating expansion rate.
Thank you. The next question comes from Rodian, Austin, Texas. He's also a professor in computer engineering, I believe. He's asking that entangled particles must come from the same source. So to transmit information, we still have to wait until one of the particles reaches its destination. Is that right?
That is correct. In fact, it's even more complicated than that. So for example, let's say you want to quantum teleport an object from A to B, right? So clearly you have to have entangled particles, one of which has to be at A, one of which has to be at B. And then the thing that you want to teleport, you bring that to A, to one of the particles. So I gave a very simple introduction because it gets too technical. So what really happens is that, yes, that other particle has immediately taken the property of the original particle. However, in the simplest case, when you entangle two particles, there are four possibilities. And therefore, without knowing which of the four possibilities those new two particles have acquired, without knowing that, you cannot unlock the other particle. So that information has to be sent, and that information cannot go faster than light. And therefore, ultimately, you are going to have to wait to get that key and then unlock and get the transported particle.
Thank you. The next question comes from Melbourne. Nazmul Haq is saying, can annihilation remove heat? Can a collapse bring opposite state of expansion?
Yes, there are speculations that our universe, right, based on how much material, how much matter there is, it is possible that our universe will actually not be an open universe or eventually a steady state, rather it will begin to shrink. And therefore we could then go through a big crunch instead of a big bang. It depends entirely on the amount of material in the universe. The visible amount of material is actually quite low. At this point, we are not absolutely sure about the amount of invisible material. So based on that, we could definitely go through a big crunch.
Thank you. Said Aziz, he has a comment rather than a question, and he mentioned that very interesting topic. My kids join and I enjoyed too. And he wanted to thank the speaker. The next question also come from Nazmul Haq. I think the Australians got a lot of questions, so I'll read the next one again. It says, if the outer portion of Big Bang has gone to disperse.
I think we already did that one.
We did that one? Okay.
Yeah.
I think we have more questions from him. Just a second. From Rodian, Austin, Texas. Planck length limit means our world is discrete, not continuous, just like information representation in computers. Any comments?
That is actually correct. The Planck length basically makes the universe non-continuous. So if we consider space, then the Planck length defines the grain, the smallest grain. Now, in physics, we also consider time to be discrete. Time is also not continuous. So there are minimal amounts, so the minimum grain lengths, both in space and time. Planck length is that grain in space.
Next question, also from Australia, says, can a superpixel of unlimited speed render the whole universe?
That is a question probably from computer science. So I don't think I really can answer that question.
We can skip this one and maybe Nazmul Bhai can answer the question,
right,
or if he wants to elaborate that. I believe Masood from Austin also. What was universe shape defined as funnel? So how that relate to special shape?
Okay, I think here the issue of funnel is actually a little bit different. That funnel is not it's not something in real space. Rather, the top of the funnel, that is the two-dimensional part of the universe, right? So a slice of the universe. And the funnel simply, if I understand that question correctly from Hawkins, that funnel really is something that connects to another part of the universe, things that we call wormholes. Now, as far as the shape of the universe before the funnel, I'm not sure I understand this question fully, right?
Masood, can you kindly unmute yourself, because I'm also not clear exactly.
Yeah, so my understanding is time, with respect to time, the universe expand. That's the funnel concept by Stephen Hawking. So according to the universe shape that you just mentioned, it has to have some boundary, but it contradicts the Stephen Hawking's theory where there is no boundary. So that's why I asked, which is that the same thing, or maybe my understanding is
no, I misunderstood your question, because I was considering the funnel that shows up in his work. That's sort of an abstract picture about time, about tunnels connecting one part of universe to another. Now, we really don't know the shape of the universe. We have a certain distance that we can see with light or light-like things, right? But remember that we don't know the total amount of material in the universe. Therefore, we don't know its curvature. So there are certain things that the universe must satisfy. There is the local curvature, the global curvature. Then there is the total amount of mass. So there are several factors that ultimately determine what the shape of the universe is or will be. We simply do not know. There are mathematical constructs that are quite difficult to visualize. I would strongly suggest that you just look up Shape of the Universe Wikipedia, and you will see the complexity that I'm talking about. So scientists simply don't know what the shape of the universe is.
So,
okay, thank you.
Thank you, Masood, also asking for the question. When I was reading it, I wasn't clear also, so probably it was halfway I told him. The last question, I think, for the Q&A, and it came into the chat session, and then maybe we can open up, unmute all, and they can speak to you directly, whoever wants to hang out and talk more and more on this. The last question, and this is also my question, so this is a very layman's question, and which a brilliant guy who is joining from Melbourne, I think, asking, why light speed will have to be constant? Why is not more or less?
Let me put it this way. The speed of light is a constant, not because of a particular reason. That's how nature behaves. Now, that's of course a physicist's way of saying, I don't know. But it turns out that the speed of light is constant. Let me give you a little bit of an idea why that's very bizarre. Let's say you are standing on a train. The train is moving to the right at a speed of 100 miles an hour, and you throw an object from the train at 10 miles an hour, also to the right. Then from the ground, if we measure the speed of that object, it will be 110 miles an hour. But Einstein's special theory of relativity says that that's not correct. It is actually more complicated than that. In fact, if you were on a super train that is moving at the speed of light, and you use a flashlight to shine light from there, then from the ground, when we measure, we are not going to see twice the speed of light. We are still going to see the speed of light. So it's a very strange behavior. Some people have tried to explain it through curvature of the universe and things like that. But I think as physicists, we really don't have a good answer as to why it is a constant. So we simply say that's an axiom with which you start. Our measurements have shown it to be a constant, no matter what we do.
Someone is typing, please. Great, thank you very much for your question. I think, does anybody wants to ask a one-on-one question? Raise hand. You can unmute yourself and ask the question. So looks like hand anywhere. That's fine. So what we can do is...
I had one question at the end, if you can
please
see. I put it on the chat.
Yeah. The laws of physics being constant throughout the universe?
Yeah, I think I heard that. But is it true? I mean, how do the physicists know? Is there any proof?
Well, you can actually do measurements, and you find that they are constant through the entire universe. So for example, what you can do, I'll give you a very simple example. Let's say you use certain techniques and find out what is happening with material that is coming out of a star. At what speed are they coming out? Their density, what kind of constitution they have. And then you can compare it with what happens on the Earth or near the Earth. And we find that those laws are constant. So we accept the fact that the laws of physics are constant. There is no guarantee that they are. In fact, there are some suggestions that the speed of light may have been different long ago. But at this point, we work on the premise that the laws of physics are universal.
I have a question, if I can ask.
Yeah, Zahid, go ahead.
So Shafiq bhai, this is nothing about physics because I'm not a physicist and I'm not really. I'm interested to hear, and that's why I stayed the whole session. But I have a question more like historical. anything about Jamal Nazrul Islam, like J.N. Islam? He was contemporary to Stephen Hawkins.
Yes, I actually do. He published some very good papers. He was in astrophysics. I have looked at some of the papers. They are very good.
Right.
But somebody asked me the question in connection with an article in Bangladeshi newspaper, one of the newspapers, and also a video that has been produced. So the video claims that he was of the same level as Stephen Hawkins. I did not see that in the published papers. Stephen Hawkins had some extraordinary papers. For example, he applied quantum mechanics to black holes and found out some very intriguing things. Now, Stephen Hawkins was also wrong on certain things. So this quantum information that we were talking about, Stephen Hawkins believed that that information is destroyed in a black hole. But people have argued and written papers that it is not destroyed in a black hole. In fact, a black hole is not something that continuously absorbs. A black hole actually evaporates due to Heisenberg's uncertainty principle. So to sort of answer your question, yes, it's a very, people who work in that area.
Yes.
They are just the best.
Yeah, when I was reading,
minds.
Right, when I was reading about him, it sounded like that he actually wrote a book about the black hole before Stephen Hawking. So, that's why I was interested that really, is it true or not?
No, that is not true because the black hole was conjectured by somebody else. In fact, there is also a very interesting story behind that. A young Indian physicist, this is long before traveling by airplanes, on his way to Great Britain. So there's a very young person. On his way to Great Britain, he read about relativity and applied it to stars. So he found some answers that were very, very peculiar. And he reported that during the conference, and the most famous astronomer of that time, he just chewed him down. So this guy, he gave up working in that area. Well, he eventually won the Nobel Prize, but for different work. Had that not happened, then this gentleman probably would have found out about black hole. I think it was Oppenheimer who actually made the conjecture at first about black holes.
Right. Thank you.
I'm Nazmul. I've got a question, if you've got time. What am I thinking that if black hole is sucking so much and if its weight should go infinitely high, so gravity is m1 times m2 divided by d square. So if something is infinitely high weight, then it will be a collapse situation. So can it happen that in black hole there are annihilations?
Well, it's something like this. A black hole forms due to gravitational collapse. Right? So that's how a black hole forms. But its mass is not infinite. Right? It has a finite mass. Now, as you were saying that it can continue absorbing things, right?
Yeah.
But it also evaporates. That was the big finding by Stephen Hawking. So there are virtual processes, which means that out of nothing, right, vacuum of space, suddenly a particle and an antiparticle will come out. And a little later, they will annihilate each other. Now, what he found out is that one of these particles could fall into a black hole, right?
Mm-hmm.
And the other one could leave the black hole, come into our universe. But now think about what has happened. Our universe has gained mass. And the place where these particle antiparticles come out, they have gone back to their original state. So what is the net? We have gained some mass. So the black hole must lose some mass. So through these virtual processes in which a virtual particle actually falls into a black hole, the black hole is actually losing mass. So all black holes evaporate.
Okay. That's
Okay,
very
great.
interesting.
So with that, let me conclude this session and I'll stop the recording now. The session will still be on. You are most welcome to speak to the guest speaker one-on-one. I do appreciate all of your time. Thank you for attending. And we are looking forward to bringing you more sessions like this where our children, all of us can benefit from this kind of 1 hour sessions. Thank you again. Please unmute yourself. You can put your video. This is just like a chit chat or hangout. So go ahead. I will stop the pause and stop button right now. Thank you.
Okay.